I'm back, and so I have written up here the formula that you're going to use in order to measure the frequency of your pendulum. And so it's going to be the number of times that it swings back and forth divided by the amount of time it's going to take it to do it in. And then you're also going to calculate the frequency of your particular pendulum using this formula here. 1 over 2 pi square root. Now this is that G thing, 9.81, and then divided by L. So we're going to go to the internet and then type in FET Pendulum Lab, and then this is what you're going to see. And then you want to click on the lab. So that's going to be this one over here. All right, so when you click on it, this is what you're going to see. So let's take a look at some of the features of the simulation. Okay, one is you can grab the pendulum and you can pull it out any distance that you want, and you can let it go. Okay, now it takes, you got to catch it there. Or down here, this, I have it set so there's no friction on it, so that if I let it go, it basically goes forever. Okay, but if I take this and I slide it over here, okay, that brings it to a stop pretty quick. Or I think you can use this red button down here and then reset it. But I'm going to put this slider over here so that there's no friction and it'll basically go back and forth forever. Now, if I pull this thing back, you see it's telling you the angle, so it's like 11 degrees right there, and then the maximum would be like 90 degrees, so I could pull it all the way back to here. Now, in the lab, you're going to set it for 20 degrees, so right about there. So that's how far out you're going to pull it and then let it go. So I'm going to put it back there so it's not swinging constantly. Okay, you can change the length of your pendulum by using this slider here. Now I would like for you to set yours for 0.7 meters. 0.7 meters. But if I move this slider back and forth, it will change the length of the pendulum. I can also change the mass of the pendulum. So I've got it set for 0.5 kilograms. So you might want to change that to 0.5 kilograms, 0.7 meters. Okay, here's the G. So G is 9.81 for Earth. But we could, by clicking on this, we could set it for the moon or Jupiter or any other planet or moon that we're interested in. But we're going to keep it set for Earth. Okay, another thing is over here you have your stopwatch. So click on that and then you got your stopwatch here. Now I would take the stopwatch and put it right next to the pendulum so that when I pull this thing out 20 degrees, then I'm right next to the stopwatch. So if I let it go, then you click on the stopwatch as soon as it comes back to you. Okay, and then you start counting. 1, 2, 3, and I would let it go 10 times. So it has to go all the way over here and then all the way back. That's 1. And let it do it 10 times, and then you can stop the stopwatch and record the amount of time it took it to do it in. I would do it 3 times and then take the average of those 3 things. You need a piece of scratch paper for this assignment. At the end of the assignment, you are going to take a picture of your scratch paper and then include that with the lab report. Okay, you don't need to insert it in the lab, but just send me a separate copy of your scratch paper so that I can see that you're doing all of these calculations. You also have a ruler. So you can measure the length of your pendulum with the ruler if you want to. Okay, so let's go back to the lab here and start filling in the chart. What the pendulum is doing is called simple blank motion. So the answer begins with the letter H. I'll let you figure it out. Write it in red. So what you think the answer is? The maximum angle that the pendulum is swinging. So when you pull it out, that's the maximum angle. What's that called? It's going to begin with the letter A. Ends with a tude. So put it together. Now we said that the amplitude was going to be 20 degrees. We said the mass was 0.5 kilograms. The length of the pendulum is 0.7 meters. The number of swings, okay, now I used the number 10. Okay, now I didn't time it for 10 swings, but you're going to do that. So you're going to fill that in. And then the measured frequency using this formula up here. So that's going to go here. And now we need to calculate the frequency using this one, and then hopefully those two numbers will be the same. They should be fairly close to each other. So what I'd like to do is a sample calculation for you using this formula, because it can get kind of tricky. So let's say, for the sake of argument, that I'm going to use a length of, let's say, 0.3. So that's going to be the length of my pendulum, 0.3 meters. So that's going to be about 30 centimeters. So it's going to be 1 over 2 pi, and then the square root of 9.81, and then divided by 0.3. So I'm going to do a sample calculation assuming it's 0.3. You're going to do it for 0.7. Okay, so we're going to take 1 over, now pi is 3.14. So 2 times 3.14, so if we get out a calculator here, or you get out your calculator, you're going to take 2 times 3.14, okay, 6.28. And then square root of 9.81 divided by 0.3. Okay, now the next thing I'm going to do is I'm going to take 1 divided by 6.28. So I could press 1 divided by, and then I need to type in 6.28 and then hit equals. But look at what I can do. Over here, you see this thing? 1 over x. So if I just click that button, it automatically does it for you. So I call this my flipper button. So it's as if I had taken 1 divided by 6.28. That's that number there. So I'm going to put 0 point, and it's going to be 1, 5, and then 9. Okay, and then there's no good way of doing this. I have to hide so you can see the number there, but I'm really here. And then let's do this part, square root. Okay, now I'm going to take 9.81, and I need to divide by 0.3, and then hit the equals, and I get 32. So 32.7. Okay, now I got to take the square root of that number. So there's a kind of an order of operations when you're doing this that you have to obey, otherwise you mess things up. So take the square root of 32. I won't do it. I'll let you do that. Square root of 32.7. and then times that number there, and then that will be the calculated frequency that you're going to put down here, and then that would be in hertz. Okay, so now there's some other things that I would like for you to do though. So if we go back, if we go down to here, so based on this equation, right here, what would happen to the frequency if it was shortened? So that means the length gets smaller. Now you can, if you want, if it was 0.7, then you can redo the whole calculation for a smaller number and see what happens to the frequency. But that's not really what I want you to do. Notice the L is in the bottom of that formula. So that means that if L was to get larger, so let's do it here, 1 over 2 compared to 1 over 10. So you see that this number got bigger, and therefore what comes out gets smaller. So if this number gets bigger, what comes out of the formula has to get smaller because it's in the bottom part of the formula. Okay, so if it gets smaller, then what should this thing do? Okay, I won't answer it, but you go ahead and put that in the lab and then try it. So all you got to do is go back to this thing here and change the length. Make the length smaller and see what happens to the frequency. So does the frequency get longer, or does the frequency get shorter? So does it do this, or does it do this? Okay, then the next thing is, so let's go back to it. So now what we want to do is, for number 5, what should happen to the frequency if the mass is increased? So change the mass and see what does that do to the frequency. Does it make the frequency go up, down, or does it stay the same? Now here's a clue. Where's the M in this formula? There isn't one. So do you notice the letter M is not part of this formula? So what does that mean? That means it doesn't depend on mass. So you could have a ping pong ball on the end of a string and a piano on the end of a string, and then pull them out and let them go, and they'll both swing at exactly the same rate, assuming no air resistance. Okay, and it's because this formula doesn't have the letter M in it. It does have the letter L, so it does depend on length, but it doesn't depend on mass. And then down here on number 6, what would happen if you pull the pendulum out further? What's that going to do to the frequency? Again, look at this formula. Notice this formula doesn't have a particular variable in it, and that should be your clue. But again, try it. So use the simulation to verify your answers for this. And then number 7, what would happen if you used your pendulum on a different planet? Okay, so change the planet this time. Change it from Earth to the moon and see what happens to the pendulum when it swings. Okay, and so based on what would happen to the frequency of the pendulum on the moon, and then change the planet to the moon and see if your prediction was correct. Okay, so we're going to take a break, and when we come back, we are going to go and look at how does a spring